So this is going to serve as an introduction to some techniques I made and the algorithm I built for automatic glider search using fractal mappings of cellular automaton. And I've been meaning to make this video for a while. So let's skip through the introduction here. We all know what a glider is because this is r/cellular automata. But here is what a fractal mapping is. The fractal mapping is the key component of this algorithm. So first of all, you need numerical mappings of cellular automata. And to do this, for 1D cellular automata, you just need to get the base 2 representation of a string of digits of the conditions, and then you find the output, because when this is run through rule 30, this is the output here. And so the mapping here would be 836, this base 2, not this in base 2, mapped to 623, which is this in base 2. Alright, so when we do this for the entire cellular automata, we get a fractal mapping mainly because of the locality of the system and the fact that each cell sort of acts locally. So here, to demonstrate the property of its fractal similarity, we have a mapping of rule 30 for 8 input cells. And then here we have one for 10 input cells. And as we can see, the pattern remains similar. Alright, so here, this is the enumeration condition, the enumeration scheme, aka the way we weight the numbers and the way we weight the positions for an enumeration thing here. So here is where we're going to actually demonstrate the search for gliders algorithm. So you create these mappings from condition 1. So we would have a first generation mapped. So we map the set of conditions to the first generation, the set of conditions to the second generation, and then the set of conditions to the third generation. And this is gliders in rule 30, so it's not really that big. They're more pseudo gliders, so we're not probably going to have a good find. But here, this red line represents the set of all gliders, all cellular automata glider formations that are left-leaning, that move to the left on a 1D cellular automata. And this represents the set of all glider formations leaning to the right on a 1D cellular automata, compared with the with 3 generation mappings of rule 30. And so what we would do is we take the close points to the mapping, and then we would zoom in on those because it's a fractal mapping, as I said earlier, and you can apply it to a larger size. And as we zoom in, we find points, and we thin down the search locations and the spaces that we actually have to search when finding gliders using this algorithm. So here we compare. Here's a little thing comparing all the search locations of if we were to go through and search every single condition versus if we were to only filter using this algorithm. So as we can see, it decreases by a significant amount, 33 million versus 4 million. And then here, this is the time to actively search all the methods, all the systems. And so what we have is about 700 seconds to search all by 8x8. And this is on a iMac. And the filtering method, because of the low amount of locations, was only about 35 seconds. And because it was numerical, it was even faster than just glider equivalence comparison. But one disadvantage is when you set the radius of search too high. So basically, how close it is to the line, and what's our tolerance here. So if we were to say, oh, I'll take anything within 16 digits of the line, then you might get a good reading on that. But if you were to only take, like, let's say, 2 digits, you'd have a lot less potential search locations, because as it evolves as a fractal shape, sometimes it will end up actually crossing the line. So we see that there are less gliders found. However, when we compare search efficiency, aka gliders found over the evaluation time, we find that brute force is significantly less efficient than filtering for the 1D cellular automata. So now let's get into how this applies to the game of life. So multidimensional cellular automata require complex enumeration schemes tailored to their neighborhoods to preserve the fractal pattern. So you can't just make a snake mapping and expect to have a fractal pattern for that cellular automata mapping. So an enumeration graph is a visualization of how you would flatten a high-dimensional cellular automata. So here we start with the center cell, and we just go around. And this is for a this is a von Neumann neighborhood. Actually, wait, let's see. This is a Moore, as it has 8 neighbor cells, and it branches off like that. So here's for a 5x5, and here's for a 7x7, and here is the positions of enumeration. So for example, 1 corresponds to the highest value, 2 and so on and so forth, and 3 so on and so forth as we continue throughout. And here we have the minimal reproducible fractal pattern, which is a square, which is basically, the black represents the input and output region, while the white represents region which can only take input. So it's measured and it's given a mapping, but it does not have any output mapping. So the mapping of the GOL, the scalable region, is seen here, and the scalable region is the key part for the fractal pattern, because you can add them together to create the mapping and enhance your size, sort of similar to 1D. However, 1D, this would be the scalable region, and you could just add it, and you would add it over and over. But here you actually have to tile. Alright, so mappings of 2D gliders. So this is a 3-generation mapping of Rule 30, and we compare it to the set of gliders, which is in orange. The Rule 3-dimensional map, the 3-part mapping, the 3-generation mapping is in blue, while the orange represents the gliders. And we can see that there already looks to be several positions for it within the respective size. So here is the time to find all 4x4 spaceships compared when we used a filtering with, let's see here, radius tolerance of 64. So if it was within 64 of the digits here, if it was within 64 of the gliders, 64 spaces of the gliders, we would record it. So here we ran it through all 4x4 potential combinations. So this is a 6x6 map here, and using brute force and then filtering, which the time to find all of them, which you could do with a search tolerance of 64, was only 43 seconds, while the time to find all of them using brute force was significantly faster at 37.28 seconds, which is, if we think about it, just over an hour. And in conclusion, if we look at this, if we look at the way it scales with the GOL, it does sort of follow a cubed squared law, where you will get more efficient in terms of time reduction using filtering as you increase in dimensionality. And because of the self-similar mappings that all cellular automata possess, like these over here, you can exploit this property to be able to find all the gliders of the system and search for them and reduce the search location significantly faster than just brute force and other methods like glider breeding. Thank you for your time.